Okay, I think we're getting close to the start time. I guess officially we are there. So okay. By the way, I will be looking at the chat window if there are questions along the way or comments that need to be made. But we will begin the journey here. So the idea of robustness is something that comes up quite frequently when we talk about design of experiments or processes in general, really. And the idea there is we want to be insensitive to changing conditions or noise factors, and we want to make sure that our processes succeed in the field when we transfer them. So when I've taught different courses, this topic seems to come up frequently, and honestly, I felt that we needed to have a little bit more complete explanation for this topic and to make people aware of the kinds of tools that can be used. So in August, I did a first webinar on the topic, and now I'm going to follow that up with some more, shall we say, intense types of studies that can be done to actually build robustness into the process from the very start. So that's really where this one's going to come into play. Let's see here. And if I could pass there we go. So for this webinar, to prevent audio disruptions, I do have everyone on mute. Again, if you need to have a comment or you have a question, I do have the chat box open, so please feel free to let me know what you're thinking there. Um, the slides for this presentation will be made available within a few days following the webinar. So you can visit our website for that. And I also believe they'll be available on YouTube in the not too distant future as well. So the first thing I'm going to do is explain a little bit of how this webinar is different than the prior one that I did for those that may have attended that one, just to kind of give you an overview of the mosaic of tools that we can offer to address the topic of robustness. And then we're going to spend most of our time going through two examples to show you how this thing called propagation of error can really help us create robust processes from the very start. Okay, so that's really what we're going to be looking at. So how is this webinar different than the one I did in August? Well, let's kind of review a little bit the whole concept of what we're getting at with robustness as a fundamental principle. The idea of robust processes are that they are minimally affected by sources of variation. Okay, so we have process factors that might wander around a little bit, right? When we set temperature for a process, what we really set is the set point for temperature, and what happens in the process may fluctuate from that set point, right? So we think we're controlling a factor, but in fact it varies. Temperature, pressure, whatever process factor you're setting. But we can also look at, external noise factors. If I'm talking about paint drying, maybe the relative humidity is an external noise factor that I really can't control, but is going to impact the process. So we have internal process factors that we're looking at that might wander around a little bit, and/or we have noise factors that might be a problem. So we're going to look at all these things. Now, in red here, the ultimate, robustness study would be one that would proactively seek to find the process factor settings that simultaneously maximize performance and yet remain insensitive to variation in both the X factors, right, our factor settings, and the noise factors themselves, right? So we're going to bake the whole robustness story into the optimization process, and that's really the key difference in this webinar versus the earlier one. So some of you may be familiar with our SCO, our screening, characterization, and optimization strategy. And in the first webinar, I pointed out that once we optimize the process, then perhaps we could evaluate that optimal set of conditions. We could evaluate that for robustness is part of what we would address in the confirmation section of our overall strategy. So So we would have screened for the important factors and perhaps come down and done an optimization for those key factors. And then we want to find out if the process is going to be robust once it sees the noise sources of noise in the field. Okay. What we're going to do now is we're going to back that up a little bit, and we're actually the concept of robustness into the optimization section itself. Okay, we're going to look at at the sources of variation as part of the optimization and try to do the optimization, including robustness. So that's what we're introducing that's new in this particular webinar. So what we're going to do in order to do that is we're going to use this concept called propagation of error, so POE, with process factors to minimize variation. And then the second example that we're going to do is we're going to bring noise factors, external noise factors into the analysis and see how we would include both. Okay, so propagation of error is the tool. So let's talk just a moment about the fundamental principle of what propagation of error actually is. So for nonlinear responses, okay, the variation in our response, or y, depends on the value of the delta x that we're evaluating. So let's kind of look at this graphic on the left. If we have a certain amount of change in a process factor setting, okay, if we're on the steep part of the slope, the error propagated with that variation is very large, okay, because it's a very steep slope over here, okay. So the change in B here propagates a significant error on the response. However, if we're operating at the flat spot, then that same amount of change in our process factor, well, when it hits a flat spot, the amount of propagated error is minimal. Okay, it's very, very small compared to down here with B. Okay, so what we want to do is want to capitalize on these flat spots to minimize the transmitted variation to our process, right? It'll be more robust. So POE is therefore a tool that can help us identify the process factor settings that can minimize the variation in our responses. Or put differently, it can help us create robustness, right? Because we have this certain amount of variation and it doesn't cause much damage. Well, that's kind of the whole point, isn't it, of what robustness is all about. So that's the tool we're going to try to build into our story today, is propagation of error. So let's begin. I'm a chemical engineer, so I tend to come up with examples that involve chemical engineering, but it's not that complex for those that aren't chemical engineers. We can definitely understand the concept. So we have a reactor that we're trying to optimize, a reaction system. And we'd like to have conversion for that reaction system that's going to be at least 90%. That's one of the criteria. But the issue with this is our reactor, it's a continuous flow reactor, so we will feed a distillation column. Now, the problem with distillation columns is that oftentimes if you have fluctuations in the feed coming into the distillation column, it can disrupt the whole process. It can make it unstable. So what we want to do is we not only want to maximize the conversion, but we want to stabilize the composition going into the distillation, right? We don't want it to drift by any more than 2 percentage points, okay? So we want high conversion, but of equal importance is we don't want that conversion to bounce around too much. We want it to be less than 2% drift. We also, just for fun, have a contaminant that is oftentimes present in the feed. And we have the option of filtering that contaminant out should it affect the process undesirably, right? So we have a lot of things that we're trying to solve here. So that's the system. High yield, but we don't want it to be fairly steady, right? So that's the goal. So since this is an optimization experiment, we're going to use a response surface design. So I will assume that the audience is somewhat familiar with response surface designs as opposed to factorial designs. And since it's an optimization design in our SCO strategy, the optimization tools are in fact response surface tools. And in this case, we will use a Stati's favorite, which is going to be the optimal designs. It seems to be a very efficient choice. And we're going to look at several factors. We have time, the reaction time, the residence time, which will be between 40 and 50 minutes. Temperature will be controlled from 80 to 90, at least the set point will be. The catalyst load, 2 to 3%. And we have a contaminant that can be present from 0 to 500 parts per million. And if it's important, we can take that decision to use that filter to remove it. Okay, so that'll be kind of an on-off switch if we decide that contaminant matters. We also have two different vendors for the catalyst that we could use, and we could use vendor A or vendor B. And the way we're going to measure that is the percent of vendor A that's included, right? It can go from 0% vendor A, which would be all vendor B, or it can be 100% vendor A and no vendor B. So that's how we're looking at that one as a single factor, the percent of vendor A. Okay, so here's what we're going to do. We're going to create an optimization response surface in the usual way, and we'll analyze it. And we'll see what can be accomplished without even including the concept of robustness. So let's see how good it can be if we don't even think about robustness. Then we're going to come back in and we will make some additional entries in our design to produce the expected amount of variation to our factors. And then we'll come back in and use propagation of error as an additional criteria when we optimize. So that's kind of the script for what we're going to be doing. So let me open up this first design. And here's what it looks like. So in the software, we have the different design choices, right? We have factorial, we have response surfaces, and I'm going to look at the optimal designs, which is the optimal designs. For those that aren't aware, we're going to let the software choose a series of data points that it finds desirable to evaluate these 5 factors to determine the impact on yield. So that's our conversion. So that's the setup. So we've entered all of the different factors. They're all continuous, and you can see the different criteria here as discussed on the previous page. So when I hit next, then it's going to recommend a 31 run design. It's going to model it as a quadratic. I have 21 required model points to look at those 5 factors, and it will include 5 lack of fit and 5 replicates. So again, we're not going to train on RSM designs. We're just going to accept the defaults now that this would be an appropriate choice to optimize this system. So I have one response, which is conversion. Okay, so we will finish this design, and there it is. So we have our 31 runs, and these are the particular values that it would have us go, collect data to accomplish. And I'm going to get the data, and I will simulate that using an existing simulation that I have, and this is going to be this one. And I go ahead and accept that. So now I've gone and collected data. And admittedly, it's much easier for me to do with a simulator than the 31 runs would be for you and I in the field, but I digress. So here's our data. So the first thing we need to do in our software, as usual, would be to analyze and create an appropriate predictive model. So I will click on conversion. I will start the analysis. It's going to recommend a quadratic model. We will accept that. I know in advance that I am going to want to remove some of the non-statistically significant terms, and I'm going to do that the simple way. So I will use auto select, and you can set the criteria and approach. I will use AICCE backward as my model reduction technique. You can use p-value backward or forward to look at it, but this one tends to work quite well for me in most cases. So I will do that. And then when I click on ANOVA, I now have a predictive model created to navigate my design space and to make suitable predictions throughout. Okay, so you can see there's some complex behavior here. My main effects are all significant. I have some two-factor interactions. I have some quadratic behavior taking place as well. Very good fit statistics. We can take a look at the diagnostics as we always do, and those look suitable as well. I mean, it's a very good fit in part due to the fact that it's a created design for training purposes. But anyway, it is a very suitable design, and we can always look at some autographs if we wanted to, maybe a 3D surface or something like that. You can see that there's some complex shape taking place, and if I change some of these other factors around, you can see that it makes a difference on the yield. Okay. So what would we want to do then once we've created a response surface design, created a predictive equation? Well, the next step would be to find the optimal conditions and to see what we can do. So we come down to numeric optimization. And at this point, what do we know we want to do? Well, we want to maximize conversion. So I'll click on conversion. I will hit maximize. And we know that we want to be at least 90%. So I'll put that as a minimum. And I hit my solutions. And with this ramp view, yes, I can do very well with this system. I have the time, the temperature, the catalyst, the contaminant. We like no contaminant. Okay, so apparently the contaminant is a detrimental thing. So right now we know that we're going to want to filter out that contaminant because we want to be zero here. And the vendor for the catalyst, it looks like it pretty much wants to be vendor A, right? It's at 96%. So practically speaking, we know we want to be with vendor A completely. And we can attain a conversion of, essentially 100%. So we can do very well. But then the next question that we want to ask is, well, what happens if I want to make sure that I'm insensitive? Remember that distillation column wants me to have no more than 2% fluctuation in my yield. So what do I need to do to account for that? Well, here's where the propagation of error comes into the story, and here's how we're going to work with that. If I come all the way back to the design, I am now going to input some criteria for my process factors to account expected amount of variation that I would see. So what we will do is we will click on the View tab here, and I'm going to go to Column Information Sheet. And this brings up, all of my factors, and here's the ranges that we set. Okay, but there's this additional column here called standard deviation. This is where now I'm going to input in standard deviation units the amount of variation that I expect could be possible. Well, so here's where you and I are going to have to put in some suitable estimates, and I'm going to use the word estimate here because this is probably all we need. But what would the standard deviation in residence time be for this reaction system, right? Well, this is where you and I would have to go do some homework and think through this a little bit, but I'm going to simply say that 1 minute is a reasonable estimate for the change in residence time for this reaction system, right? I might have some fluctuations in flow rates, that sort of thing, so that the residence time in the reactor, I feel that, based on process knowledge, that a 1 minute standard deviation is suitable for the residence time. And likewise, temperature, right? I look at my temperature control system and the fluctuations, and maybe I actually measure what happens inside the reaction system. And I also reach the conclusion that a 1 degree temperature change, standard deviation for the temperature that the reaction system actually sees would be a suitable estimate for what's taking place there. And the catalyst percent. Well, I take a look at how I'm metering that in, and I reach the conclusion that based on the specs for the meter, if you will, and the flow rates involved, that maybe that could be 0.05, right? So the hardest part to this is really, you and I, with our process knowledge, being able to make appropriate estimates for the standard deviations that would be expected. Now, for the contaminant, since I already know that I don't want any of it and I will use the filtration system, I'm going to put 0 there because we're going to lock that in at 0. That is in fact what the contaminant level we want. So we're going to filter that out. That's okay. And also we're going to choose the catalyst vendor A. And so I don't need any standard deviation there because I'm going to choose 100% of A, right? So I don't need that. So really, time, temperature, and catalyst are the only ones that I need to make estimates for this standard deviation. All right, so once I've entered that, something so I can go back to the process layout. So now when I come into the numeric optimization, I have something new that appears. Because I've entered the standard deviation, I now have the propagation of error for conversion that I can use as part of my selection optimization criteria. Okay, remember that's what we're going to do now. We're going to optimize using POE as part of the criteria. So let's set this up. So what do we know? We know that the contaminant we're gonna filter that. So we're gonna set that equal to 0. Okay, so the choice here I'm gonna set that equal to 0 because we're gonna use the filtration. Vendor now I am going to set that equal to 100 because we've decided that vendor A is the better option. So we're going to lock that in. The conversion, well, we still want to maximize that. We want that to be at least 90. But now for the conversion, the POE on conversion, well, we want to minimize that. This is where the magic comes now. We're going to minimize that, and we know that we have an upper bound here of 2 percentage points. We want that to be no more than 2 percentage points so that the distillation column won't be haywire. So now when I hit solutions, here's what we have. So we're going to change the time, the temperature, and the catalyst are all honed in. We've got the contaminant at 0 because we're filtering it. We've chosen the catalyst supplier to be 100% A. And now what we're doing is we're balanced the variation in our conversion against the absolute conversion. And so what we find is, well, before we took POE into consideration, we could attain essentially 100% on the conversion. But now, if we want to keep it stable, right, robust for the distillation column, well, we can keep the POE for the conversion. We can contain that to less than 2 percentage points, 1.9, like we want it to be. So the distillation column will run effectively, but our conversion drops down to around 92%. Okay, so we're trading these two things off. It's suboptimal for conversion, but it's stabilized so the distillation column can handle it. Okay, so it will be robust. It'll be a robust set of, a combination of conversion and it'll be robust for the distillation column, and that's how we attain it. We use POE and use that as part of the criteria. Okay, so that's the principle of POE and how we can use it in the optimization process. So let's go back to the slides then. So what did we find? Well, if we don't pay attention to POE, we get 100% conversion. We also know that we want 100% vendor A, so we can lock that in and do the filtration to keep that contaminant out. However, with those conditions, the expected variation of conversion would be around 2.9%, and that's higher than the 2% that we actually want. So what we're going to do then is we're going to include the POE criteria. We introduce the standard deviations, the expected amount of variations that we would see on the process factors. We went and put that in, and now when we use POE as part of the criteria, capping that at 2 percentage points, yep, we find that our yield drops, but we can attain constrain the variation to a desirable level. Okay, so that's how POE can make this process more robust. Now, So really, if you think about it, what we just did is we looked at uh, process factors, variation in process factors, so our x's, and we use that part of the criteria. Now, what if we have external factors, things that we can't control, noise factors, z's, if you will? What if we have those? How are we going to include that in this overall concept? Well, that's the next exercise. So let's take a look at this one. So in the previous example, we treated a contaminant as something we could get rid of, right? We could filter it out, okay? But what if the contaminant would be an ongoing source of variation? It's going to be a noise factor, right? It's going to be what it'll be, and it's going to wander around on us, and it may cause us some trouble. So in this next example, I'm going to trade out the vendor factor, and I'm going to add, another contaminant just to make this more interesting. So now I have two contaminants. One goes from 0 to 500 parts per million, the new one from 0 to 100 parts per million. And we're going to say that those two, we can't control them. They're just going to be noise factors. They're going to occur in the field, and we just have to figure out how to make our process robust against those two noise factors. So we're going to treat these noise factors as we did in the previous example. However, when we optimize, we're going to set these two contaminant levels at some nominal value, like let's say halfway between the min and the max. Okay, so we're just going to lock it in. So like the first one went from 0 to 200, 0 to 500 parts per million. So what we'll do is we'll lock it in, I'm going to say halfway through. We're going to lock it in at 250. But then we're going to introduce a standard deviation to show us that that number may float around a little bit, right? So it's going to be somewhere between a minimum and a maximum level. So so how are we going to come up with the standard deviation? Well, let's remember that we're using these as kind of approximations to what we're going to see in the field. And probably the easiest thing to think about is if I have a min and a max, like this contaminant may go somewhere from around 0 to 500. Uh, the standard deviation, a good estimate for standard deviation might be something like 25% of the min-max difference. And that comes from kind of a rule of thumb principle that says when we quote, if we ask someone, how much does that vary? What they typically quote back to us is equivalent to about 95% confidence level. Well, that's kind of like plus or minus two standard deviations. So I'm going to use that as a rule of thumb to say, well, if it's going to go from 0 to 500, that's confidence. I'll divide that by 4. So I'll say my standard deviation is going to be about 125. Okay. So 25% of the min-max difference is a suitable estimate in most cases for what the standard deviation would be. Then what we're going to do is we're going to shop around for the most robust process factors that minimize the conversion, maximize the conversion and minimize the propagation of error, including that contributed by the contaminants. So let's go into that one and see how we do it. So once again, it's going to be an optimal design within the response surface world. So this one's just a little different now. We still have the time, temperature, and catalyst. But now I have two different contaminants, right? The first one, as before, goes from 0 to 500. And the second one we're going to introduce that goes from 0 to 100, okay? So I will hit next. It's once again going to create a 31 run design. We'll go ahead and finish that up. And here's our design. Here's what it's going to want us to do. Now it's important that during the DOE itself that we can control these factors as indicated, right? So these noise factors, at least during the DOE, we have to be able to control them so we can execute the study. We recognize that in the field that will be an uncontrollable factor, but for the time being, in the lab or pilot, wherever we're doing this, we're able to set these contaminant levels so we can study them. So that's an important consideration for when we do the designed experiment. All right, so I will go out there now and I'll get my data. This one is going to be exercise 2, and okay, so then we get our data. Well, as before, we can go ahead and create the model. So let's go ahead and do that. We'll start the analysis. It's going to be quadratic. I will do the same thing I did before. I will use some model reduction, AICC backward, to get rid of terms that are not helping us make a good predictive equation. So we weed out the insignificant terms, unhelpful terms. And we again get a statistically significant model, very good fit statistics, etc. Right? So there's our predictive equation. You can always take a look at the diagnostics, and that's all good enough. One of the things I will point out that I think is interesting in this particular case study, if I look at what I'm going to call the perturbation, which is how much each factor is influencing things, my final two factors, my D and E, D is one of the contaminants, and that one is from low to high. It actually is degrading the conversion. E, on the other hand, is an interesting one because that's actually helping our conversion. That would be, somehow it's buffering the system, maybe it's blocking a side reaction, whatever it is. A little bit of that particular contaminant is actually, showing some benefit to the system. So it's an unusual contaminant because we like it. Anyway, so we have competing. The contaminants are competing against one another as we do this. Okay, so we've done that. Now what we want to do is come back to our design, and here we will go back to our column information sheet, and once again we're going to put the relevant standard deviations into the system. Well, the first three are going to be just what they were before. So one on temperature, one on time, one on temperature, 0.05 on the catalyst, right? And again, where you get those from? Well, you, the process expert, have to make some reasonable approximation for what you think that would look like. Okay, and this is my guess for this system. All right, so what am I going to do for the contaminants? Well, I like to take 25% of the span. So 0 to 500, 25% of that would be 125, and 25% of the span, or from 0 to 100, well, that would be 25. So that's the standard deviation that I think is going to be, kind of equivalent to 95% of the cases would be represented with those inputs. Okay, so now we have everything we need in order to use POE as part of the analysis. So now we come down to numeric optimization, and let's go through and set our criteria. So the temperature needs to be in range. The catalyst needs to be in range. Now we're going to have the contaminant 1. Now, how are we going to set that one? This is where the noise factors. This is kind of a key point to making this work. What we're going to do with the contaminants now, because in the field they're going to be what they're going to be. So what I'm going to do is I'm going to lock them into, let's say, their midpoint. Okay, so that first one, contaminant 1, goes from 0 to 500. Well, I'm going to set that equal to halfway, so 250. And then what's going to happen, because I put standard deviations in that column view, it's going to allow that to kind of float around, plus or minus, right, given the standard deviation. And so we're just going to input it as its midpoint, and we're going to find the impact that's going to happen as that floats around through that standard deviation. Contaminant 2, we're going to do the same thing. That will be set equal to halfway, so 50, right? So that's kind of the nominal value. We're going to let it, we're going to pin it at its nominal value, and then let the propagation of error, take us into what we would expect to take place in the field. All right, so the conversion, we want to obviously maximize that, and we want to be at least 90. Let's see, I guess we can put 100 here, I think. we'll see. POE on the conversion, well, what do we want to do with that? Well, we want to minimize it. Now in this case, I can't get to the 2 because the lowest the lowest I was able to accomplish was 2.3. So what we're going to do is, well, if you can't get what you really want, let's find out what you can get, right? So I will crop that in to make that no higher than let's say 3 percentage points. Okay, so we will try to keep it under 3. So I will hit my solutions, and here's where I end up with this one. So now I have my time, my temperature, and my catalyst settings. My contaminants kind of nominally at its 250 level, right? Because I've locked those in. Okay, so we're accounting for the fact that those contaminants will be present at some level. But now, given the variation that we're expecting in all of these things, the conversion that I'm expecting is going to be 91, 0.5-ish. And really, I can just barely attain that 3%. So I can't get to the 2, but now I got to go talk to the distillation column folks and say, can we live with a variation of 3? How can you tune your distillation column now to accommodate a little bit more fluctuation than we want? Okay, but at least we found the most robust, the most stable set of conditions given the variation that we expect in both the process factors and these contaminant noise factors. Okay, so using POE, the variation and conversion caused by my noise and process factors can be brought into the optimization. Since in the field we don't get to choose the noise factor levels, in this exercise we set them to an appropriate nominal value and let POE take it from there to mimic the real world behavior, right? Because we put the standard deviation. So it's kind of like a Monte Carlo simulation where, yeah, we put the nominal value, but it's going to float around and it's going to take that into consideration when it does the optimization. And when it did, we have a balance between conversion and insensitivity to noise. In other words, we've optimized the system to incorporate the concept of robustness. Okay. So let's wrap this up a little bit. So, we want to create process flexibility from the start. That's the whole goal of the approach that we're taking in this webinar, as opposed to evaluating whether a system is robust once we've optimized it. We want to include the concept of robustness as part of the optimization criteria. In general, so kind of looking at what we've talked about through the 2 webinars now, robustness studies improve the chances of success when a process, or even a mixture, is released to the field. So we can improve the chances of success by acknowledging that we're going to see variation in the field that we may or may not have seen in the lab or pilot system when we created these things. We want to make sure that we're robust against what the product will see. Variation in process factors, and/or noise factors can be included. Right, so we can look at the variation in our time and temperature, et cetera. Or in this case, remember, we looked at the contaminants that may appear or not appear on any given day, and we don't get to control them. They're just going to be there when they are. Robustness studies can be very simple. In the first webinar, we talked about Plackett-Berman designs, which are often used to demonstrate that the process would be robust against certain factors. And ideally, in that case, we're hoping or expecting to see no impact. We're going to demonstrate that we are insensitive to certain factors. Plackett-Berman designs get a little bit more complex if, in fact, we do discover that there's a factor of significance because of the highly aliased structure of Plackett-Berman designs. We might not know what exactly is causing the problem. We just know that we have a problem. So they're very good designs when we expect no impact. It gets a little more complicated when we do find an impact. I suggested an alternative to that in my first webinar would be to use Stady's MR4 designs, because that's going to give us a little bit more insight on what exactly the cause of the variation is. And that's probably good if you have a limited number of factors that you're trying to evaluate. What did I say, 6 or 7 or 8 or something like that. If you've got 20 things that you're trying to evaluate, or upwards of 10 even, you're probably going to need to use a placket Berman and just deal with the potential alias issue. And you can do different techniques like fold over designs to try to get at that a little bit. But if you have fewer factors, like maybe 8, maybe the MR4 design might be a good choice. Robustness studies can also be a little bit more complex, like we looked at in this. You can actually include the robustness concepts when it's being optimized by capitalizing on this propagation of error tool. And that's the differentiating point between the first webinar and this one, is now we're actually including robustness as part of the optimization step. Now, Mark Anderson has a webinar, DOE for on-target results with minimal variation. This is an interesting approach where he's going to have a second response, right? So in this, let's imagine we were looking at conversion in my little example. And let's imagine we collected 5 or 6 data points at each one of the different runs that we did. And we measured a standard deviation for those 5 or 6 data points that we collected. Well, so he would have measured the conversion response and the variation observed at a set of conditions, and he would use that as a second response. So you could optimize conversion while minimizing the standard deviation, right, as a separate criteria. So that's another idea that one could look at. And in the end, what do you do? Well, the key here is you get to pick, right? So you got to look at the goal of your experiment and your budget and decide what the best choice in the end is actually going to be, right? DOEs can be expensive. They can get extravagant. We looked at we have 5 factors here with 31 runs. You have to decide, what you can afford and what's going to be the most effective use of your budget, and what really the goal of your experiment is. Okay, so all we can do is to make you aware of the tools and the techniques that exist, and encourage you to think through them and to make the best choice for your particular situation. If you need a little bit more training and understanding for DOE in general, if some of what I said, has gone past you, or you're not really sure what a responsive surface design is compared to a factorial design, we do offer more complete training packages. So we can look at modern DOE for process optimization. That would be where we look at factorial designs as well as responsive surface designs. And if your world is formulations or mixtures, we have a training course available for that as well. And that's just to also say that everything we talked about robustness, you can include for a mixture design. Because when you make a mixture, you might have some variation in the ingredients, right? You're metering different, in manufacturing, you're metering different quantities into a system, right? You're not able to reproduce the lab formulation precisely, right? You have some inaccuracies. Well, all of that can be brought into robustness studies as well, right? So these can apply to mixtures as well as processes equally well. And that is the end of today's webinar. So we really want to encourage you to think through what's going to be most useful to you, and capitalize on DOE as much as possible to make the most of every experiment, right? Glean all the information you can out of the work that you can afford, and to put it together. So I don't see any questions in the chat box. But if you do have questions from this point forward, feel free to email me at richard@statease.com. If you do have sales questions or want to explore DOE software more completely, contact sales@statease.com. And that is, unless I'm looking one more time at the chat box to see if there are questions. There are not. So that is where we're going to end today's webinar. And I do thank you for your attention and interest in the idea of making your processes and products more robust. Thank you.